Good morning, everybody. Welcome to Science Show and Share. We're so excited to have you on this edition. We are the Series Center for Education, Engagement, and Evaluation, and we connect educators, learners, and communities with environmental and earth system science. We are part of Series, which is the Cooperative Institute of Research in Environmental Sciences, and the cooperative part is our relationship with NOAA, the National Oceanic Atmospheric Administration. So we're so excited to have you here today. We're really excited to have Dr. Jen Kay with us today to talk about her work. We're going to hear from John Griffith, the author of Data Puzzles, and he's going to talk a little bit more about our Data Puzzles program. Thank you so much for joining us today. We're so excited to have you here. Teachers in classrooms, welcome to Science Show and Share, and I'm going to pass it off to John.
Thanks, Daniela, and thanks all for being here. We've got adult learners in classrooms from across the country here joining today for this event. We want this to be an interactive event, so if you wouldn't mind, we're going to be using the chat extensively today, adding links from Dr. Kay's presentation, hopefully facilitating some question and answer at the end. So for folks that are here, classrooms that are here, please feel free to introduce yourselves and where you're joining from in the chat. And as questions come up for you during Jen's presentation today, please feel free to drop them in the chat and we'll get to them in the last 10 minutes of this event, making sure that your questions are answered. Like Daniela said, I'm John Griffith. I'm the developer of a resource called Data Puzzles. These are resources that combine classroom-friendly data sets with these research-backed teaching practices to support students in making sense of phenomena. And in this case today, we're going to be talking about a phenomena called Arctic amplification, the fact that the Arctic is warming more rapidly than the rest of the world. This has been a phenomena that I have been fortunate to work extensively with Jen to develop resources connecting students to this phenomena for about 5 years now, Jen, which kind of blows my mind that it's been that long. But really been fortunate to get to work with Jen and am inspired by her commitment to connect all types of learners to Arctic climate science and the inequities of climate change through her work. Developing resources with me and presenting at events like this. So Jen, we'll turn it over to you. We'll have you speak for maybe about 15, 20 minutes, and then we'll open it up. We've got classrooms from Maine, Alaska, all across the country today. So I want to make sure that everyone has an opportunity to get their questions addressed in the last 10, 15 minutes. So that's it for me. Take it away, Jen.
Yeah, good morning, everyone. I am Jen Kay. I'm a professor at the University of Colorado at Boulder, and it's just such a pleasure to be able to chat with you this morning about some of the kind of basics of the research that I do in the polar regions and globally. So we're going to talk about Arctic warming, and we're going to use both observations and models. So we're going to use data from multiple sources to try to understand what's going on. And we're going to address this really core issue that where greenhouse gases increase the most is not where it warms the most. So we'll get into why. So I'm going to start with just an image from space. I know some of you don't really think about the polar regions much. You know, maybe you're going about your busy day and, you know, you're not thinking about the Greenland ice sheet, which, you know, has a lot of land-based ice. It's pretty high elevation. We have some other types of ice in the Arctic too, the Arctic Ocean, which we're looking down on. So the North Pole is actually covered with frozen ocean. That frozen ocean is called sea ice. We can also see the surrounding land. I heard there were some folks from Alaska on the call. See if you can spot Alaska in this, looking down at the North Pole from space image. There's also clouds, and clouds tend to be bright, and they're reflecting the incoming sunlight. We're basically using the sunlight so that we can observe what's going on from the satellite. So this was taken on June 21st of 2024, so just this last June. But I pulled up this image, which was taken October 24th, 2024, so just this week. And all of a sudden, you can see there's this big hole over the North Pole. And you might be asking, well, why is there a big hole over the North Pole? Like, why can't the satellite see anymore? And this brings up another fundamental difference between the high latitudes and maybe the other latitudes of the planet, which is that, we have polar night. So for a large fraction of the year, there's no sunlight. And that means that we can't see what's going on with our eyes. And same thing with the satellite we're using, it can't see down to the pole. So this just brings up some of the interesting things, the kind of physical drivers of what controls the seasons and the extreme cold at the high latitudes, but also just sometimes that it's really hard to observe what's going on up there because some of the tools that we sort of rely on from kind of our lower latitude intuition don't always work. So another thing that's very different about the Arctic and the rest of the globe is that the Arctic has warmed a lot more than the globe. So these are observations showing the amount of warming over the 20th century and into the early part of this century. And what we can see first in black, the line there is the global warming. You can see it's about 1 degree warmer Celsius. And we can also see that the last full year that we had on record is the warmest year of the entire season, the entire record. So that's global warming. Then we can see in red the Arctic and a couple of observations here. First of all, if we look where it's gone from, so about -1 surface warming to +3 surface warming, we can see that the Arctic has warmed about 4 degrees Celsius. So that's, maybe 4 times more than the globe. We can also see that the Arctic has some more variability. It's kind of going up and down a little bit more. And that's consistent with the Arctic being a much smaller fraction of the total surface area of the planet. So there's some factors that influence the Arctic that don't influence the global mean. So there's a lot that we could talk about with these observations, but the main thing I want us to take away now is just that the Arctic just seems like a lot more sensitive, right? It's warming a lot more. It has more variability than something like the global mean. So why? Why is the Arctic warming more than the rest of the world? The answer to that, is something that we could get into, but I won't in big detail here because it's actually part of a lot of the resources that John and I have developed, so we can put you in touch with those. But the Arctic warming more than the rest of the world is because basically there's processes that are unique at the high latitudes that cause the high latitudes to just warm more. And one of the examples of a process that is unique to the high latitudes is we saw all of that, land and ocean-based ice in that visible image at the beginning. And all of that ice, when it melts, it basically darkens the surface. And we all know a darker surface can absorb more sunlight than a light surface. And so that leads to what's called the surface albedo feedback. And that is one of the main amplifiers of warming in the Arctic. And those processes that are involved there, kind of melting of snow and ice and darkening a surface and more absorbed sunlight, those are something that are unique to something like the Arctic just because it has a lot more ice to begin with. There's still a lot of active research, though, in why the Arctic is warming more than the lower latitudes and what the implications of that warming are. I mean, I have a current grant from the National Science Foundation that's part of what's sponsoring this particular engagement with you all this morning. And in that grant, and along with a lot of other scientists, we're using both observations and models to understand the processes underlying climate change and variability. And the observations can be incomplete. The Arctic is a faraway place. Sometimes some of our tools from lower latitudes don't work so well. And by models here, I mean numerical models based on physics. And there's this atom, all models are wrong, some models are useful. When we're trying to represent the physical processes that control the climate of the entire planet, we have to make some approximations and simplifications. So by definition, those models are going to be wrong. But that doesn't mean that they're not useful. And we really try to engage those models with the observations to try to inform our understanding of the science underlying warming. So let's talk a little bit about ways to observe the Arctic. You can go there in situ, so you could go in a ship, or you could potentially launch, a weather balloon from the ground over land. So those kind of measurements are great, but they're pretty sparse. It's hard to regularly have them, and they tend to be pretty expensive to make. Satellites are an amazing source of information. Since about the late 1970s, we have information, for example, where the ocean is covered with ice. That's really, really useful. And then another type of information we can get are from ice cores. So we can go up on the big ice sheets and basically look at all of the different layers of snow that have accumulated year after year and make measurements in those layers of snow. And it gives us kind of a backwards history of what's been happening with the climate there. So there's lots of ways to observe the Arctic, and we use all of them. So here, this is an example of a satellite data record. So this is the observed Arctic sea ice loss. It starts in about the late 1970s when we had, between 7 and 8 million square kilometers. So this is an area. It's the area of the ocean that's covered with ice. And we can see in recent years that that area has been a lot less, somewhere between 4 and 5 million square kilometers, and sometimes even dipping into the 3s. So this record, is a multi-decadal record, many, many years of observations, is one of the pieces of evidence that we have that we're losing ice, and also that ice loss may be contributing to more warming in the Arctic than at lower latitudes. Just to give some perspective on what that looks like, again, this number, million square kilometers, is an area. And here we just have, North America, and we have the area of the Arctic sea ice on one of the record minimums, which was September 20th, 2012. And then we have basically where the ice would be, what area it would cover over North America, and kind of, more normal or typical conditions. So we can see that there's, a lot of variability in how much ice cover there is on the Arctic Ocean, but that this loss of ice is, it's equivalent to a pretty big difference in area. It's like, moving the border with Mexico to, the middle of Kansas, like big changes in where the ice cover is. We can also look at these as Arctic maps, and I encourage you, teachers, and with your classrooms, to look at some of the resources, make your own maps here. You can monitor this in real time, looking at where we have anomalies. That just means departures from that long-term average, and where those are happening in the Arctic. So we can see for September 2024, a lot of blue colors. That's indicating less ice than normal in a lot of the central Arctic. And then if we look, for example, in March, that's when there's the most sea ice cover. It happens at the end of the winter, when we've had all of that winter time to freeze. We can see basically there's lower than normal and higher than normal sea ice along the sea ice edge, which has now moved into, for example, the North Atlantic or the North Pacific. So again, a great resource for you to check out with your students. Look at the data, see what's going on and how it varies by month of the year. Another exciting thing I have to mention is that I'm part of a satellite team that launched a new pair of satellites this past May and June, whose mission is to study Arctic heat loss to space. These missions are doing well. We're collecting the first data from them. I think it's an example of just how we're continuing to learn and explore our planet. And this mission, funded by NASA, called Pre-Fire, is just one example of that. Okay, so we talked about observations. Let's talk a little bit about model. Now, this word sometimes can be confusing because I think sometimes there's a different meaning in kind of everyday language versus what us scientists mean. When I say model, what I mean is something that's basically a bunch of equations that are describing physical processes, typically using laws of physics or representations of processes, as approximated from observations. And these models can be very simple. They can be the kind of thing you solve on your laptop computer, or they can be solved on supercomputers. So if you have millions of lines of code and you need, lots and lots of processors, your laptop computer is not going to be enough. And these models are really cool because they enable you to ask questions that we can't with the observations. For example, we can ask, what would happen if we remove this process from our model? Or what would happen if we changed the amount of greenhouse gas in the atmosphere? How would the climate system respond? And then we can use that as a basis to kind of inform and understand what's going on in the observations. So that kind of brings us to this kind of key set of maps that kind of underlie this question of why is the Arctic warming more than the rest of the planet? And what does that warming in the Arctic and globally have to do with increased greenhouse gases? And I think if we look just first at the top map, what we're looking at here is basically the warming. So we're asking, what does the warming look like? What is its spatial distribution? And this is a map that's produced based on a numerical model simulation, but we have observations of this and they look really similar. And what we can see is the Arctic is warming more than the rest of the planet, as indicated by those darker red colors. We also see things like the land warming more than the ocean, consistent with differences in heat capacity between the land and the ocean. So this is, very similar to what we would see based on our observational records, but it's from a model. So then you're going to ask, well, how did you force this model? Like what process changed in the model to cause this warming? So in this case, this simulation, this model integration was driven by a number of factors, but one of the key drivers or key forcings was the increase in atmospheric carbon dioxide, which was approximated using data from the last century. And so that's what's shown on the bottom, the change in surface atmospheric carbon dioxide. Now, carbon dioxide is a well-mixed atmospheric greenhouse gas. So if I emit some carbon dioxide in Colorado, it doesn't just stay in Colorado, it actually mixes over most of the planet. But if I continually increase a lot here, the concentrations are going to be a little bit higher over me. So if the only source of carbon dioxide was me in Colorado, all you would see would be an increase over Colorado, and then it would spread to the rest of the planet on a mixing timescale of years. So here, what we can see is that the change in surface atmospheric carbon dioxide is consistent with large industrial centers where a lot of human activities have been increasing greenhouse gases like carbon dioxide in the atmosphere. So we can see North America and Asia and Europe as kind of main drivers of this increase. So what's really interesting is that these two maps, they don't look the same. Where you've had the most increase in atmospheric carbon dioxide is not where you've had the largest warming. In fact, the Arctic is a region with very little increase in local atmospheric carbon dioxide, and yet it has warmed the most. So this is the foundation of the data puzzle that we put together, and I hope that you have fun talking about it and thinking about it with your students. And so with that, I'm going to wrap it up, and I'm happy to take any questions. I just have a summary slide here, some take-home messages. The spatial pattern of surface warming does not match the spatial pattern of surface greenhouse gas increases. In recent decades and over the 20th century, greenhouse gas increases by humans are really largest over Asia, Europe, and North America. Yet with these increased greenhouse gases, the Arctic is the place that's warmed the most. So thank you so much, and happy to take some questions.
Oh, John, you're muted right now. I'm trying to unmute you, but I'm having a hard time. Thank you, Jen, so much. That was informative. We are so grateful to have you here today joining us and sharing all this incredible work with us. It's really, really powerful stuff. We'd love to hear from our classrooms with any questions that you have. So please drop them in the comments here, and we will start to take those questions. John, what were you saying?
I was saying that the chat is full of links right now, and if you were unable to click on those links and explore them during this 20-30 minute talk, which would be expected, we'll follow up with an email with Jen's slide deck, as well as links to all of these resources that Jen referenced, so you can explore them on your own time after this call. We'll take this first question from Patty Brown up in Alaska. How does the Arctic data compare with higher latitude data in the southern hemisphere? Thinking about Antarctica.
Ooh, that's a great question. So one of the hardest places to make in situ or just like in-person measurements is actually the Southern Ocean, the ocean that encircles Antarctica. That is one of the most data poor, data sparse regions in the entire planet. By comparison, the Arctic is relatively well observed. You know, in Alaska and other land-based places, it's easier to make measurements. And also, there's been just much more of a presence from humans in the Northern Hemisphere and the Arctic. And so that has also helped with some of these kind of in situ measurements. I guess the other thing to say is the ice cores are really valuable, and Antarctica, we have opportunities to collect those over a much larger area because the Antarctic ice sheet is just bigger than Greenland. So that's a source of information that we have in the Southern Hemisphere that we don't have quite as many of in the Northern Hemisphere. And those ice cores in Antarctica go back almost 800,000 years. So that's a really valuable, really direct measurement of, for example, what the greenhouse gases in the atmosphere have been for almost 1 million years.
And Jen, I was thinking along the same lines of thinking about the Arctic and Antarctic, these different polar regions. And like we talked about, the Arctic is warming more rapidly than the rest of the world. But when I'm looking at that temperature map, it doesn't seem like the Antarctic is warming as quickly as the Arctic. Can you talk about why the northern pole is warming faster than the southern pole? Why is there this difference?
Yeah, that's a great question, John. And I think the main thing to remember is that even though they're both polar regions and they both have, for example, polar night, they're very different geographically, right? The Northern Hemisphere, we have in the Arctic, we have an ocean over the North Pole, right? And then we have that encircled by land. So, you know, Russia, Alaska, you know, Greenland. Whereas in the Southern Hemisphere, we have this huge ice sheet, Antarctica, sitting over the pole, and it's much higher in elevation. So, you know, maybe not as easy to melt because it just starts colder. And then it's surrounded by the ocean, the Southern Ocean. And the Southern Ocean is actually one of the oceans that's a real buffer for climate change. It's taking up a lot of heat and putting that heat down into the ocean. So there's just some real basic geography differences that mean that we wouldn't really expect these two poles to warm or react in the same way.
Great, thanks, Jen. That's so interesting. Think about the geographic reasons for the differential warming. Miss Mick's class has a question. How long have you been in the Arctic with your research? How long have you been doing Arctic research? Do you go to the Arctic to do your research? And a question about your most recent pre-fire grant. How long is that grant for?
Yeah, great questions. So I first went to the Arctic when I was a graduate student doing my PhD, and that was for a month in October of 2004. So almost 20 years. I've been to the Arctic multiple times, but a lot of the research that I do uses satellites and numerical models. So I don't always have to go to the Arctic to understand it. And so, yeah, I try to use all of these different data sources. It's obviously super exciting when you get to go there in person, but we do a lot of great science with data and physics that don't require us to go to the Arctic. And then pre-fire, oh my gosh, such an exciting satellite mission. It was first funded in 2016. So we have been planning for this for a while, and we were delayed by the pandemic. There were some issues with putting the engineering and launch and all of these things together during COVID. So we were super excited to launch. It's a pretty short mission because it's using CubeSats. And so the technology there is like kind of newer and more experimental, but also less expensive. And so it's very exciting to see what data we get. And hopefully, we'll be up in space for a couple of years. We were launched in June, and we're just so far really happy to have observations coming back down that we can work with.
And Jen, what will you do with those satellite observations? So you mentioned the satellites measuring heat loss to space. Yeah. What are you going to do with those observations?
Great question. Yeah, first, just put them in the context of the other observations that we have, right? So a little bit of black body physics here, like things that have higher temperatures emit more long wave radiation or infrared radiation. They lose more heat, basically, because they're hotter. So this is just a way of measuring that's a little bit more precise because we're looking at different wavelengths. But we have satellites that have been up in space, since 2000-ish, that measure all of that heat. So we're trying to put everything together. What's the total budget, the total energy budget, and how does having some more information about the heat loss at very specific wavelengths, how does that relate to kind of the total heat loss that we've been observing?
Wow, pretty cool, Jen. Any other questions from folks, classrooms in the chat? We'll mention that I'm going to send a follow-up email. And you can feel free to direct questions to me as well, and I can forward them to Jen. Are there facilities where students can see actual ice cores?
Yeah. You could Google NICL, the National Ice Core Laboratory. And there's places that ice cores get stored all over the world, all over the country. But NICL is the National Ice Core Laboratory. And if you happen to be close to it, maybe you could go visit it. And also, you could always ask them if there's a facility near you that has ice cores. I know the building that I work at the University of Colorado has ice cores in it. So if you happen to be close to Boulder, you could always reach out to me and John, and maybe that'd be a fun field trip to do with some of the teachers we engage with, John.
Totally.
Yeah,
totally. We'll just do one more question and thinking about feedback loops. We're talking about the Arctic warming more rapidly than the rest of the world, the loss of sea ice contributing to this ice albedo feedback loop. How might the release of methane from melting permafrost also contribute to warming in the Arctic?
Great question. And this is also an example of research that's ongoing, and we're collecting a lot of information both on the ground and trying to measure that from space, because you can see methane from space from some of the newer satellites that we have. Obviously, methane is a super potent greenhouse gas, so releasing it from melting permafrost would amplify the warming and really increase it. And that could be an example of a local source of a greenhouse gas, which is not something that we've really seen so far. So that's really a great question.
Cool. This all blows my mind, Jen, to think about satellites measuring greenhouse gas concentrations of methane and carbon dioxide. And you're measuring energy at different wavelengths. at all different levels in space, all to capture what's going on in the Arctic, and we're doing this all over the world to improve our understanding of climate change. So it's really mind-boggling. Thanks for breaking it down for us here today, and for all your help contributing to the resources that we develop.
Yeah, thank you, John, too. These data puzzles are so fun, and I just love that they're inquiry-based and that people get to ask questions. I feel like this idea of like living and breathing science is exactly what I want people to walk away from this webinar with. Like, we're not here to just like tell you how it is. We're here to tell you why we think we know what we know, and how we're doing it, and help you kind of think about it through your own eyes too.
Yeah, thanks, Jen. And if folks want to learn more about data puzzles, or we're running another webinar focused on offshore wind energy, wind farms of the future. My colleague Elise Thurber will be leading educators through that resource. November 13th, we'll add a link in an email for folks that might be interested in learning more about that particular data puzzle. And we're going to continue to try monthly to lead educators through data puzzle lessons, and then have the featured scientists in those resources join us for these virtual calls. So we'll reach out about some of those future events, and look forward to working with you all and learning with you all more in the future. Thanks, team. That's it for us. Keep in touch.
Thanks, everybody.
Bye, Jen.
Email us with any questions if you have them. Our website is posted here in this banner, so please come and explore and check out what else we have going on. Have a great day. This video also will be live and ready to view with your other classrooms immediately. So I hope you get to enjoy this with some of your other classes today.